Okay, today we're talking about decibels. By the end of this lesson, you will know how the number of sources and the intensity are related, how in, intensity and the perceived volume is related, and how perceived volume and decibels are related, and a good review on logarithms. Here we go. All right, so give that one a shot. Thumbs up when you have a guess. Have a conversation.
I was about to say E.
Okay. Correct answer is E. Folks, I really hope we can have this skill like just hammering you all year. Like I really okay. So E, you triple that, you have to square it. So 1/9. Okay. Here's my analogy. Well, not analogy first, but picture this. You throw a rock in a pond, the waves go out. Okay. How much energy is associated with that has to do with this equation, the intensity. Okay. So here's the analogy. Let's say this stool is the source. Okay. And as the analogy is jelly is energy. Okay. If I'm at the source and I take a spoonful of jelly, I just eat it straight away. Okay. If I take some distance away, I have that same spoonful of jelly, same amount of energy, I spread it over a saltine cracker. Okay. Some distance away, I take that same spoonful of jelly, same amount of energy, and I spread it over a piece of bread now. Some more distance away, I take that same spoonful of jelly, same amount of energy, and now I'm spreading over pizza crust. Okay? Pizza. Sometimes desperate times calls for desperate measures. All right. But does that make sense? You're just spreading it out thinner and thinner. Okay? That's what this equation communicates. Okay? All right. Give this one a shot. Have a conversation.
Nah, it's definitely 64 million.
Okay. Correct answer is C. Okay. The number of sources and intensity Those go hand in hand. Okay. This is an intuitive relationship. Okay. One of them is 400, two of them is 800, three of them is going to be 1200. It's a linear relationship. Makes sense to us. That we have no problem with at all. Okay. Number of sources and intensity go hand in hand. Good with that? Okay. And this is where the intuition stops. Okay. Tell your neighbor. Correct answer is C. Okay, this is a crazy thing about the hearing, the human hearing. When you go and say, when you hear something like, "Oh, that's twice as loud," and then you go to measure the intensity, it turns out to be 10 times the intensity of the original volume. It's crazy. We're like, what? Like, I don't know. It's just how it works. Okay, we've measured it, and we're like, oh, dang. Okay, you got to figure this out now. Okay, so 10 times the intensity. Tell your neighbor. Okay, correct answer is yes. Okay, correct answer is C. Okay, 10 times the number of sources. Intensity and number of sources go hand in hand. Okay. Okay, correct answer is D. 10 times the number of sources. All right. We're going to do kind of proof of concept. This isn't the greatest demonstration, but it's all right. So get out your cell phones and, all right, these are legal. I am. I'm going to set you up. 400 hertz frequency tone. Okay. You're looking for a 400 hertz frequency. I've got a one. I found one that's a minute long. It's a light blue screen. YouTube, Sonic Electronics. 400 400 hertz frequency. There we got that. Go ahead and press that. Turn your volume all the way up.
This is what Ivy League universities you can get
Let's
into
get past the
with
commercials.
3.6 GPA. 90% of
400, 400, 400 hertz frequency. 400 hertz frequency. Everybody get it past the commercials. You can play it, and then once you got it going, and go ahead and hit pause. Put you in the center of the classroom so you can kind of hear this. Okay, thumbs up when you're good. Thumbs up when you're good. Okay, here's what we're going to do. There's roughly 20 of us. Okay. Ava and I are going to play ours. Okay, go ahead and everybody hit pause. Okay. Ava and I are going to play ours. This is going to be 2 guitars playing. And then I'm going to have everybody turn theirs on, and it's going to be 20. And listen to how loud it gets compared to just 2 of us. Okay? Ready? Go. Just us 2. Okay? My volume's all the way up. Yours as well. Okay? Everybody play. That's about twice as loud. Okay? Hit stop. Okay? And put your cell phones away. Okay? Now, a quick disclaimer, this wasn't the greatest demonstration because you are different distances away from the source. Okay? But that was kind of like twice as loud-ish, right? I mean, you're not going to, well, it technically, okay, yes, I know, but like kind of close, okay? So, give that one a shot. Tell your neighbor what you think. Correct answer is A. Why do we divide by 10? Well, we just do. It's a half the volume. Half the volume. It's a tenth of the number of sources. The tenth of the intensity. Good with that? Okay. Now, this relationship screams logarithmic. Right? Okay. When I was in your shoes, going into this test, going into a math test, logarithms test, I'd memorize this. Okay, I'd be like, okay, the x goes the other side, or no, the y goes the other side, the x goes up, and the b gets bigger. And I could write this equation on the top of my test, and then I could just, I aced this test. It was like easy. I had no idea what I was doing. Zero comprehension. I just knew the pattern. And I knew how to plug stuff into my calculator. And I'm like, I'm so smart. No, I just zero understanding. Okay. My hope is, my goal is to give us some understanding of what this is, what a logarithm is. Uh, Now, but not back then. Okay. So assume base 10. Okay. We're just going to do base 10. Okay. If I have 100, 10 to the what gives you 100? 2. Yes? If I say, if on my calculator, if I say log 100, that's going to yield 2. Okay. Okay. 10 to the what? Ooh, that's a question mark. 10 to the what? Okay. That is 10 to the 7th. So if I say log of 10 million and I put that in my calculator, it's going to spit out what? 7. What does the log button tell us? It focuses on the exponent. 10 to the what power? Okay? That's the whole point of logs, is looking at the exponent. That's why we do this. Okay? Whole point. So, let's say I gave you to figure out the answer to that isn't going to be easy. Like, sorry, you can't do it without a calculator, but I want you to estimate. What do you know it's between? Just think about it. Don't say it out loud, just think. What do you know it's between? Think about it. Tell your neighbor what you think it's between and how you got there. What does it have to be between? What does it have to be between? What am I giving you a high five for? Yeah, okay. All right, we know it's between 1,000 and 10,000. Okay, so it's somewhere between 3 and 4. Does that make sense? Okay, it's not 3.5, right? It's not intuitive. You need a calculator. You've got to plug that in. I did this last hour, so I know it. 3.7. Okay, you've got to use a calculator. Logarithms are not intuitive unless you like work with them like a ton, and then I guess it would be. But we don't. Okay. Now, um, decimals, decibels is a logarithmic scale. Okay. So Richter scale, we find logarithmic relationships all over the place in science, in nature. The Richter scale is a logarithmic scale. So you're like, man, we got hit with an earthquake of on 4 on the Richter scale, and then we got a second wave that was 6. And initially, you just think, oh yeah, that's just 2 more points. Every time you go up in the Richter scale, you multiply your intensity by 10 times. So going from 4 to 6, that's going from 4 to 5, that's 10 times. Going from 5 to 6, that's 10 more times. That's 100 times more intense. That is intense. Okay? Does that make sense? All right. So, here we go. There are 4 blaring car horns producing a total sound of 70 decibels. What is the intensity of this sound? Okay. So, we're going to be employing this equation that you just learned about. We're assuming log base 10. Okay. So that's our equation. So you have 70 decibels is equal to 10 times log. This is what we're looking for, I, and threshold of hearing. This is a constant, just a set value. That's given. I will give that to you. Threshold of hearing. Okay. So that's how we take the numbers out of this and plug it into that. Okay. Solving for I, we have 7. Okay. How do I get log over the other side? How do we get log over the other side? How do I get log over to the other side? Okay, you could either go put that over there because you know math. You know the trick for math. Or you go second on your calculator, log, which gives you x or 10 to the x power. Yes? Good with that? Okay. So getting the log to the other side, you go second log button. That brings that over. Inverse log. Okay. And then, so that's like 1 times 10 to the 7th. So that becomes 1 times 10 to the negative 5th watts per meter squared. Yes, no, maybe so. Okay. So that is, how does that math sit with you? Is that okay with that? Okay. So that's 4 car horns blaring. What is the intensity of 1 car horn blaring? Okay. So this is 4. What would the intensity be for 1? Tell your neighbor how you'd figure that out. Okay. This one is intuitive. This one makes sense. This is like number of sources and intensity. If this is 4 of them, I want to find one of them, and you just divide by 4. You okay with that? Okay. So I know this is incorrect way to write this answer, but I think it's going to be more educational. Okay. So it's 0.25 watts per meter squared for the intensity of 1. Good with that? It's a fourth of what we had. Okay. Now, the follow-up question is, how many decibels is that? So 4 of them was 70. I want you to just guesstimate what the decibel for 1 car horn. Okay. Let's calculate it. So we're using this equation. Okay. So we have an intensity of 0.25 times 10 to the negative 5th over 1 times 10 to the negative 12th. That's the constant. Okay. So this is 2.5 times 10 to the 6th. Okay. You need a calculator for that. That is 6.4. So this is 64 decibels. How does that compare to what you estimated? 70 decibels was 4 car horns blaring. 64 is 1. Okay, you probably got it wrong. Okay, it's not intuitive. That's the point. You have to use a calculator. Okay. Okay. Good with that? All right. So we have one car horn blaring is 64 decibels. If I doubled the perceived volume, like, whoa, wow, that's twice as loud, and I took a decibel reading, what would it say? Tell your neighbor. Correct answer is A. This is the third relationship. Okay. First relationship is number of sources and intensity go hand in hand. Okay. It's the first relationship. Second relationship is, whoa, that's twice as loud. That is 10 times the intensity. If you double the perceived volume, you multiply your intensity by 10 and the number of sources by 10. Okay. If you hear something that's twice as loud, like, whoa, that's twice as loud, you add 10 to your decibels. Add 10 to your decibel. That's the third relationship. That's what we employed here. We went from 64, we doubled, like, whoa, that's twice as loud. And we measure that. That's plus 10. We added 10 to our decibels. Third relationship. Good with that? Okay. Thumbs up when you have a guess. Tell your neighbor. Tell them how you got there. Okay, what do you say? Dangerous dinosaurs. How do we do? Okay, when we double the perceived volume, we multiplied the number of sources by 10, and we added 10 to our decibels. Okay, good with that? Now, I'm going to say something that if it doesn't stick, just let it fly on by. Okay? But some of you are like, hey, why are we adding this logarithmic? Okay, so decibels, deci in the metric prefix means 10. Okay, it's deci, not bells, just decibels. Okay, so if this was purely a logarithmic scale, we would just add 1 to it. Every time we go up like a value of, we're multiplying by 10, but because it's decibels, we add 10 rather than add 1. And that's what this 10 in the equation is for, is to convert it from bells to decibels. Okay? If that made no sense to you, just let that fly on by. Okay? All right, give that one a shot. Thumbs up when you have a guess. Converse. Tell them how you got to where you got.
Where are you getting the 2? No.
Correct answer is? Correct answer is C. Okay, check it out. As we go from 95 decibels to 85 decibels, what do we do to our intensity? We have 1/10 of that. We divide by 10. Yes? Okay. As we go from 85 to 75, we're dividing by 10 again. So divide by 10, divide by 10, dividing by 100. Does that pattern make sense? Okay. Now, this chart here shows us every row we are doubling the perceived volume. Like, oh, that's twice as loud. Oh, that's twice as loud. Oh, that's twice as loud as that. Oh, that's twice as loud as that. Oh, that. Okay. So at the beginning, okay, we can argue that I don't care. These good, bad examples, whatever. Okay. Watch this. Forget this. Don't worry about this. Okay. Every time we double the perceived volume, we add 10 to our decibels, we multiply by 10 by intensity. Okay? Good with that?
At the
Okay.
bottom, it goes from 10 to 0 to 10 to the negative 2 instead of 10 to 2. Is that a mistake?
Right here.
Yeah.
That is a mistake. Good catch. Man, I've been doing this for years and no one's pointed that out. Nicely done. Nicely done.
Because one is to the 3. Wouldn't it be to the 4th?
That would be to the 4th. Nicely done. Man, I gotta find a new chart. Okay. Ava. Yeah, so it would they should have a 130, but they don't. 1 times 10 to the first, and then 150 would be 1 times 10 to the third.
how's that? 140 to 2.
They had third. It should be to the fourth, and then it was negative. So it's okay. So does everybody see that? That makes sense. That relationship there. Okay. This is the audiology report of the human ear or human hearing. Okay. Down here you have frequency. So this is low, really low. This is really high. Okay. And this is volume, intensity. Okay. Really loud. Okay. This is the threshold of hearing. Notice that we can hear higher pitch uh, frequencies softer than we can hear lower pitch. I'm more sensitive to that. Okay. Threshold of pain, though, this is like kind of like it's just loud across the board. Okay. Okay. When I was making this lesson years ago, this was revolutionary to me. Like I didn't know this. We're all aware that loud sounds hurt your hearing. That's like okay. But it's also a factor of time. Okay? Loud like really loud sounds like whoa and like things that make your ear ring and like that's damaging to your ear like your hearing. But for example, mowing the lawn, I would not inherently say a lawnmower is inherently loud. It's medium loud, but it's not like, oh my goodness, shut that up, it's so loud. It's not like threshold of pain loud. But if you're exposed to that for a long period of time, that's damaging to your ears. How long do you listen to music? The longer you listen, the more it thrashes. Or like the more it's damaging. Like is that like it's not just loud, it's loud and how much time. Okay, so something that you want to that's not too loud, but if you expose yourself to that for a long period of time, not good. Okay, so that's right when you say warning. This is too loud. This set for 85 decibels is like the safety. Yeah, I know you do.
Like whenever I'm in the car, like I'm listening to music too loud, like my phone will go off and be like, the sound around you is at 90 decibels. Staying around this sound for too long, like for 30 minutes, could cause like hearing damage.
Yeah.
Yeah, then I turn it down.
I know, it's crazy.
There. Sometimes I do if I'm really having a good time.
Right. Okay. So, yeah, you get that. This is just for funsies. Like, where does humans rank in terms of our range of hearing? So, you got a worksheet to do tomorrow.